All right, I'm super stoked about this particular set of notes. My name is Mr. Kingsbury. I am an Algebra 2 teacher, and currently our unit is talking about inverses. Wow, that got really bright. Sorry about that. Let's see if I can adjust the light a little bit here, maybe to help. I'm hoping. We'll see. Anyway, today we're going to talk about composite functions. Specifically, our essential question is, what is the composition of two functions? How do I use it? And there's really kind of a lot here that I need to unpack. So let's start by reminding machines. You put something into the machine, it does something, one thing or two things or what have you, and then another thing comes out. For example, I love this example. I have a machine at home. It sits on my counter. Anything I put into it, it toasts. I like to call it a toaster oven. If I put bread in, it toasts the bread. I get toast out. I stick in a raw bagel, it toasts a bagel. What comes out? A toasted bagel. I stick in a frozen waffle, what comes out? Delicious waffle goodness. It does one thing, it toasts stuff. No matter what I stick in, that's how it affects the thing that goes into it. Well, that's what functions do. They do the same processes over and over and over and over and over again, like a machine. And because of that, typically, when you put in a specific x value, you get out a specific y value. Now, sometimes you can put in two different x values and get the same y value out. But most of the time, you put in one x value, you get out a very unique y value that goes with it. So thus far, when we've talked about functions, what we've really had you do was, for example, we'd have you take a defined function and then use it in a couple ways. So let's say that f of x equals, I'll just keep it simple, 3x plus 7. All right, 3x plus 7. This is my function. This is the name of the function. You could substitute y here if you wanted, but that's what this is. This is f of x. That's how we say that. This is function f. That's its name. It's not a variable. What we're doing is we're plugging values in for x, and we would use this one of two ways. Okay, I might say, what does f of 3? So I would replace the x in the 3 would be, you know what, let's change it from 3 so it's not as confusing. Let's say, what's f of 5? All right, so I would replace this x with 5. So instead of it being 3 times 5 plus, instead of it being 3 times x plus 7, this would become 3 times 5 plus 7. And if I were to do the multiplication, I get 15 plus 7 is 22. So f of 5 equals 22, essentially giving me the ordered pair 5, 22. I can also use that in reverse. I could say something like, hey, what is, I'm trying to think of one off the top, what does x equal? Well, in this case, f of x equals something. I want to know 37 out. What did I put in the machine? So how do you handle that? Well, you replace the f of x with 37. So this would go from being f of x equals 3 times x plus 7 to 37 equals 3 times x plus 7. And then this one you would solve. So I would subtract 7 from both sides. So on the left hand, 37 minus 7 is 30. On the right hand side, 7 minus 7 is 0. 3x plus 0 is just 3x. So now I have the equation 3 divided by 3 is 10. So I get the x value 10, which creates the ordered pair 10, 37. In either case, what I'm doing is I'm saying, look, when I stick 5 in here, when I take 5, multiply it by 3 and add 7, I get 22. When I take 10 and multiply it by 3 and add 7, I get 37. That's really what functions are about. And the reason that they're so unique and important in math is because they have this property that every x value is paired up with a unique y value. Every time we stick in a specific x value, we get a specific y value back, and that doesn't change. And that can be very, very useful. So now, what is a composition of functions? Well, first of all, you have to have more than one function. That's essential here. And what you're essentially doing is you're both functions together. So to continue with my machine analogy, this is like using both a washer and a dryer. You can use them separately, right? Like, for example, when I get back from the pool with my son and my wife, we throw all of our towels in the dryer so that they can be dried because they're wet from drying us off. So we throw them in there and they get dried, right? We don't necessarily have to wash them first. We can just throw them in there to get dry. Similarly, I have some articles of clothing, my wife actually does specifically, that need to be washed, but they need to be line dried or hung to dry or air dried. You don't stick them in the dryer. So I could use them separately if I wanted. But a lot of times we'll use them together. And that's really more for the machine analogy than for math. With math, you've got two different functions that have been defined and you're going to use them together. But much like the washer and the dryer, you use them together. You stick something into one and it gives you something back. And then you take what you get out of that machine and you stick it into the other machine, and then it does something, and what you get out is different as well. Just like you take dry, dirty clothes and stick them in the washer, and when they come out, they're clean and they're wet. Then you stick them in the dryer, and when they come out, they're clean and they're dry. So they've gone into the washer dirty and dry, and they come out clean and dry. Well, that's what we're doing here with functions. So this is kind of our mathematical version of a washing machine and dryer, all right? First, you have to have two functions that are defined. So why not just stick with 3x plus 7 as f of x? But let me define this other function as g of x equals x. So for starters, what we'll do is give you values. You plug into one, and then you get a value out. You plug it in the other, and then you get a final value. And we have a specific way to write that, and that's going to tell you what order to do them in. So for example, let's say I want to know what f of g of 2 is. Well, you start on the inside and you work your way out. So I would start by sticking 2 into the g function. So I would find what is g of 2 first. Well, that's going to be 2 squared plus 1, which ends up being 5. 2 squared is 4. Plus 1 is 5. So g of 2 is 5. Now I'm going to take the thing that came out of my g function, and that's what's going to go into my f function. This goes here. So I put a 2 in, and I see what happens, and then I take the result, and I'm going to do something with that. So now I'm plugging 5 into the f machine. I'm going to multiply 5 by 3 and add 7. So I get 3 times 5 plus 7. And we happen to know from up above what that equals, but I'll do the math again. 3 times 5 is 15, plus 7 is 22. So f of g of 2 equals 22. I may ask you what the reverse is. I may go, what is g of f of 2? Now, a lot of people mistakenly think that if f of g of 2 equals 22, then g of f of 2 will also equal 22. Not necessarily the case. G of f of 2, that's the mathematical parlance. So I will expect you to be saying things like that in class. Let's figure out what g of f of 2 is now. So we're, again, starting in the middle, right? So we'll start with f of 2. That means I'm going to find out what f of 2 is by taking 2 and sticking it in the f machine. It's going to be 3 times 2. I'm really getting tired of my pencil breaking. Plus 7. 3 times 2 is 6, plus 7 is 13. Then I will take that 13 and I'll put it in the g machine. G of 13 will be 13 squared plus 1. 13 squared is 169, plus 1 more is 170. So g of f of 2 equals 170. And you can see the two are not the same. So don't assume that just because it equals something going one way, you're going to get the same thing if you reverse that. The other thing that I may do, and I'll just show you one quick example of this. I won't do it both ways. But another thing I might do is instead of a number, I may ask you, well, I'll do two different things. I may ask you to put in an expression. So, and I'll try and keep this fairly simple. Let's say f of x equals 2x minus 5. And let's say g of x equals, I'm just going to stick with x squared, keep it kind of simple there. You know what, let's go x squared minus 3. Why not? I may ask what does that equal? Now, I'm going to treat this exactly the same as I would those previous examples I showed you. There's just going to be one snag. See, on the previous examples, when I plugged this in, all I was dealing with was numbers. So everything was a like term, and I could continue to combine and change things. In this case, I may not have some like terms, so I may end up with multiple types of terms, and I'm going to have to know how to deal with that. And actually, I'm going to switch this just because it will make the calculation a little bit easier, okay? Trust me on this. If I didn't, we'd have to square a binomial, and I don't particularly want to do that. So let's do f of g of 4x. So first, we need to know what's g of 4x. Now, I'm going to start this just like I did the other problems. I'm going to replace the x in the definition with 4x, right? In fact, you know what? Let's do it like this. So what I have, my definition, g of x equals x squared minus 3. And what I'm going to do is I'll replace the x with 4x. Now I have to square that. 4x squared would be 16x squared minus 3. And there's nothing else I can do. Because there's an x here, I can't combine these. So this is what I'm getting out of the g function when I plug 4x in. So this is what I need to put in the f function. So now I'm going to find f of 16x squared minus 3. Now the f function takes what we will distribute this to. We get 32x squared minus 6. And then don't forget the minus 5. And then the last thing we can do is we can combine these like terms, negative 6 and negative 5. That's going to give me 32x squared minus 11. So what does f of g of 4x equal? That will equal 32x squared minus 11. That's a little more complicated because that variable in there keeps us from being able to combine as much stuff, so that gives us more terms that we have to juggle and deal with and manipulate. The other thing I might do is just ask you the x definition, the g function inside of the f function. So let me see if I can show you what that looks like, okay? So the f function is 2 times x minus 5. And what I'm going to do is remove this x, and I'm going to put the g function inside where the x went. The g function is x squared minus 3. And then once you do that, then you simplify it as much as you can. Distribute, collect like terms. Those are really your two moves, or distribute and collect like terms. I don't know that we're going to get all that much more complicated. There may be a little factoring, but I doubt it. So let's distribute the 2 here. We get 2x squared minus 6. Don't forget minus 5. And then that will equal 2x squared minus 11, because we can put negative 6 and negative 2x squared minus 11. There's kind of a finesse there, I get it. And we're going to have to practice that a lot because you're manipulating some things there. But I promise once you do it 2 or 3 times, it will start to make more sense and you'll be able to understand it. The interesting thing is, just going back to my original equations, and I won't make you write anything down about this, but I think this is interesting to note. Back here when we were doing these composite functions, if I wanted, I could put these together. I could find out what f of g of x equals, whatever that new function is, and then plug 2 into that. I'll get the same answer. And some teachers would require you to do that. Others don't. We in the Algebra 2 group decided we weren't going to make you do it that way. But I just thought it's an interesting way. If I asked you what plug 2 in here and see what you. But I'm going to encourage you to do the first way, where you just plug the numbers in. So it would seem like that is pretty much all the things you can do. There's actually two, is you can use the composition of functions to find out if two functions are inverses. And let me remind you, inverses undo each other. Now, we talked about this in the last set of notes. We talked about how multiplication undoes division, addition undoes subtraction, and we did some inverse table, given ordered pairs, etc., etc. Well, one final thing you can do to see if two functions are inverses is you can find their composition. The thing is that in order for two functions to be inverses, both of their compositions must equal 0. So this is how I'm going to define it, and this is going to be a little mathematical. Two functions, f of x and g of x, are inverses if f of g of x equals x and g of, do a couple examples here. The first one I will do a function. So let's define f of x as 2x plus 1. And let's define g of x like that. I do believe that will work. So are they inverses? Let's find out. First, we need to know, is f of g of x equal to x? So this is how we would do it. We would take our f function, right? And then we would stick this whole thing in for x here. So we got x minus 1 over 2. So 2 times plus 1 and negative 1 plus 1, well, those cancel out as well. So you get x. It's like I set it up that way. Then we have to check and see if g of f of x also equals x. Sometimes it works one way and it doesn't work the other way. I don't think that you're going to get any that are like that, but I thought I would mention it. So we're going to take our g of x function, or definition, which is x minus 1 over 2. And then we'll stick our f of x definition inside where the x goes. So we'll put 2x plus 1 right there in the top where the x went. So x plus 1 minus 1 divided by 2. And let's simplify. And I realize this is in parentheses, but that's really just so I could show you where I was substituting. So if I get rid of the parentheses, I have 2x plus 1 minus 1 over 2. And look, 1 minus 1 is 0. These cancel out, and I'm left with 2x over 2. And look, 2 divided by 2 is 1. 1 times x is x. So f of g of x equals x. G of f of x equals x. So yes, they are inverses. That's pretty cool, right? Let me give you one more example, and I'm sure you've already guessed these are not going to be inverses. So last example, and then our notes are done. Let's say f of x equals, let's just keep it as 2x. No, let's say that it is x divided by 3 minus 8. And let's let g of x equal 5x. So are they? Let's find out. So let's find out what f of g of x is. So I'm going to take x, divided by 3 minus 8. And I'm going to replace the x part with 5x and go from there. And truthfully, there's not a whole lot of simplifying that goes on here. This is just 5/3 x minus 8, and it doesn't get any simpler. Truthfully, I don't even really need to go any further. It certainly doesn't equal x here, so I can stop. Just to prove my point, though, let's find what g of f of x is. All right, so that would be 5 times x over 3 minus 8, which would again equal 5/3 x minus 8. So they equal the same thing. That's interesting. But they don't equal x, which means no. They are not inverses. We're going to do some more of that in class. We'll do more practicing, and hopefully you'll get the hang of it. It's really not too difficult, I promise. It just takes a little bit of practice for the manipulation of the terms, but for the most part, it's pretty straightforward. See you in class.